Yeah, thank you. Thank you for attending. I hope you can see my screen okay. I'm Themos Kalos. I'm Chief Scientist and Managing Director for Orion Delta Technologies, and I'm going to talk about the industrial applications of the metasurfaces. Now, I gave a talk about 10 years ago in a metamaterials conference in Denmark, talking about the hype cycle of metamaterials. And I introduced the concept, not of the hype cycle. This is something that's well known, and I'm going to briefly summarize here for people that don't work in marketing much. But it basically plots the hype of a technology over time. And there is usually a few 5 stages. There's some kind of technology trigger that creates a spark. Then there is what's called the peak of inflated expectations on what you can do with that technology. Then this usually dies down. There is a trough of disillusionment, but things gradually pick up back again with the slope of enlightenment, and then you reach a plateau productivity, which is usually lower than the peak was. And I'm going to show you how that looked like at the time for metamaterials. Before I do that, just a couple of words about what we do. Orion Delta Technologies is a SME based in the UK. It was founded only last year. There was a team previously with Metamaterials Inc., which was a NASDAQ-listed company, over 200 people working on metamaterial applications that unfortunately had to shut down operations last year. So we've picked up some of the technology and know-how now and continuing the effort. This brings us to about 50 or more years of commercial expertise in developing and manufacturing transparent meshes, metamaterials, and in general structured functional films, which includes metasurfaces. We do more than optics in terms of the frequency range. In general, we develop optimized hardware components for various OEMs, and these include primarily building demonstrators, design, prototyping, integration, and then we work externally with manufacturing partners for volume production. I'm not going to go through all the expertise, but I just marked in red quickly to show that we're also quite good at metasurface design and fabrication. And we cover the typical like design simulation, prototyping, integration, sampling, and characterization in-house. Now, coming back to the topic of metasurfaces, 10 years ago, I presented what I thought was at the time the hype cycle for metamaterials. So what this looked like was left-handed media was the technology trigger in the 1990s with a negative refractive index. Then about 10 years later, in the mid-2000s, with the work of John Pentry and David Smith, we had the clocking and perfect lensing applications, and this did create a lot of hype and brought many researchers and interested parties in the field. Very quickly, within a few years, this died down because it was very difficult to scale up these ideas and the losses were just too large. And in 2014, I proposed that metasurfaces, which at the time were just coming around, would be the future of the metamaterial field, and this would lead us to commercial applications. So in the remaining of this talk, I would like to explore some of these commercial applications that have come, with 10-year insight, and I think it's quite successful. I'm going to bring some examples from the industry, but also metasurface we've developed ourselves. Obviously, there is MetaLens. I think is the most popular commercial application of optical metasurface, where they've managed to replace multiple lenses and diffractive elements with a single structure. And this is used for polarization and infrared imaging. Lumotive is also doing very good work. They've integrated metasurfaces for LiDAR, and they also include liquid crystal for some tunability. The difficulty in such products is that the metasurface metamaterial is just one component, but you actually need to build the whole system to demonstrate to the end customers that this is something useful. Another example from the UK, from Kinetic, there's been a film that basically it has an infrared signature, and the purpose here is that when there are helicopters looking at chasing vehicles with an infrared camera at night, it's not easy to distinguish like the police vehicles from the perpetrators. But by adding this film on the police vehicles, then at night you are able to tell which car is which. So that's a very interesting practical application. Some of the work that was done at Metamaterials that since was acquired by Authentics, this is on banknote security. The idea there was to create plasmonic metasurfaces on microsurfaces, and these produce diffraction effects, coloration and motion and other structures that are good for authenticating banknote and other security products. The benefit here is that you are able to replace the traditional micro lens with a plasmonic nanostructure, a much more compact and with much higher degree of flexibility with regards to what kind of effect you can achieve. Now moving on to stuff that we are working on currently, we have transparent metallic metasurface antennas, and one example is using these antennas as heaters and communication elements in LiDAR. The optics part of the application here is that you want to mitigate diffraction that inadvertently comes in when you try to install any kind of grating or surface in front of an optical component. So there are techniques here you can use to mitigate this diffraction so that the LiDAR sensor can operate efficiently. Another interesting application on the AR side is what we call eye-box optimization. So if you look at the top right, you have a traditional reflective element on an AR glass that, as many of you know who are in the AR VR industry, is difficult to translate between different people because we have different, different eyeballs in different places and so on. So the idea here is that you use a metasurface made not out of nanoimprint, but out of a hologram. And this allows you to basically create masters that are much cheaper, and then you can create individualized masters basically at a reasonable cost so that you can mix and match each person with the reflective and optical combiner that's best for them. In combination with this technology, there is capability to integrate this inside lenses instead of on top of lenses. It's basically you can cast a lens around your optical combiner element, and this allows basically to do conventional post-processing with all the ophthalmic techniques and not have to worry that you have a very, very sensitive metasurface element that you have to protect and worry about. So that's my quick round trip of applications, and I'll close off with outlook, what I've seen in the last few years and where things are going. So a couple of points. There is definitely a shift from bulk metamaterials to surface metamaterials and metasurfaces. This is maturing, especially for infrared applications where they're a bit more forgiving in imperfections. The companies that are very successful have managed to leverage CMOS foundries. This is very important. But still, the costs must reduce. As a starting point, if you're starting in this space, you need to be able to produce an element, I would say less than $1 per square centimeter in terms of surface area. I mean, there is obviously a lot of variation there, but that's roughly the order of magnitude you should be looking at. This means there are more manufacturing advancements required, and as everyone, I think, here agrees, especially for the visible frequency range, this is still a bit of a challenge, and I think it will remain a hot topic for the next 5 to 10 years. And just to close off where I think the innovation needs to happen, what are the issues currently with metasurfaces? Obviously, limited bandwidth is difficult to produce very wide on metasurface without many artifacts. The efficiency is still relatively low, especially in transmission modes. People tend to prefer reflective elements for that reason. The tuning still couples right now amplitude and phase. These two cannot be controlled independently very well. There is limited tuning range, especially in the phase. So ideally, you want to have very easy, 0 to 2 pi control, again, without many artifacts and with good efficiency. And I think this is because the tuning mechanisms right now, there are not that many. There are only a couple of things you can try, and some new ideas are needed there. And finally, many of these nano-imprint and other manufacturing techniques are incompatible with CMOS technology. I think the reason some of the companies have been more successful are the ones that have managed to integrate their designs and piggyback with CMOS technology that has been around for decades and has been cost optimized. So we need to find ways to tighten this integration, in my opinion. And with that, thank you for your attention, and I'm open for questions.
Thank you, Timos. Thank you very much for